function. So let's try one more. This time, absolute value function. Same values. Are we going to get the same thing? And so basically what ends up happening, let's see what happens when we multiply these guys by a half, 3, and negative 1. This time, it shouldn't change anything. I mean, if history repeats itself, or like the previous ones, we should get the same values. And so I'm going to start with y equals the absolute value of x. And so if this is the case, I pick my x values, and I'm going to pick my traditional ones, negative 1, 0, and 1, because in absolute value, they're going to just all turn positive. And so I get my, and I know it's absolute value, so I should know it at this point that it is a v-shaped graph. So I would get something that looks like this. There's my parent function. Now, what's going to happen when we multiply by a half? Well, if history is anything for us, it should say it should flatten this graph out. So if I take a half of the absolute value of x, remember we got to do what's inside the function first, and then we'll find then we multiply by half. So I'm going to pick my same values again. And negative 1 is 1, cut in half is a half. 0, cut in half is 0. And 1 is still a half. And so you can see that this time I'm at right there about a half. And when I graph this thing, it should be basically the same. And you can pick more points if you don't like just going off of what I have here. I'd pick more points if you don't believe what I'm going with here. But you can see that this function, half of square root of x, is half as tall as the other one. So again, we got smushed because we multiplied by a number between 0 and 1. So again, we're going to do 3 times the absolute value of x, and if history repeats itself, it should be pulled up and be steeper. So I'm going to pick my same values, negative 1, 0, and 1, because they're the easiest to deal with. Again, take the absolute value of negative 1, positive 1, times 3 is 3. Absolute value of 0 is 0, times 3 is 0. Absolute value of 1 is 1, times 3 gives me 3. So I'm at 0, 0 again. And again, remember that I'm not adding or subtracting anything, so that's why this graph isn't moving from 0, 0 at all. It's just going straight through 0, 0, going straight through the same. It's at the same beginning point because it's not being added or subtracted anything on there. So if we're adding or subtracting, then the graph might move left or right. So then the question is, what's going to happen when we multiply by negative 1? Well, if we multiply by negative 1, as we have seen before, it should flip it over the x-axis. Should make it be the same as the black graph, but flipped over. So if I'll pick my same values, negative 1, 0, and 1. Absolute value of negative 1 is 1, but I'm going to make it negative, so I get negative 1. Absolute value of 0 is 0, but make it negative, so it's 0. And absolute value of 1 is 1, but make it negative. And so when I plot my points, I'm here at these 3 green points, and you can see that my graph is going upside down. So some things you should pay attention to, that if it's being multiplied by a positive number, the thing will always go in the same direction as the parent function. If it's multiplied by a negative, it gets flipped over. If it's multiplied by a half, it ends up flattening out. And if you multiply by a number bigger than 1, it ends up getting steeper like this. So finally, these are the conclusions you can make, and I'm going to let you guys do those. So you should go through and answer these questions. I've already gone over these plenty of times when I've in my notes here. So I'm going to let you do that on your own. So pause it and fill them in. It'll probably be on your notebook check. And so then finally, we want to write the equation and sketch the graph of x squared that has been vertically compressed, meaning wider, by a factor of 3 and translated down 4 units and reflected across the x-axis. So this is the type of questions that you get, and these are kind of typical of what we're seeing. And actually, let's see if I've got any down here. I might want to try some of these. I've actually got some other equations that I think we should probably do before we do the out. So let's move these guys up and see what happens here. So this one, it says write an equation and sketch the graph of a x squared that has been moved 2 units up and is 2 times wider than the parent function. Well, we found out that if I want to move things up and down, I add to it. So my equation that I'm going to write is y equals x squared plus, we want it 2 units up, plus 2. So then if I want the thing wider, that means I have to multiply by a fraction that is between 0 and 1. Wider means that the thing, wider or compressed or anything like that, means that the graph is going to get squished. And so we got to multiply by a factor of whatever the 2 times, that means it's a half the size. And so that would do it. And so just a quick little sketch is I'm going to move it up 2 units. And then when I go over 1, I'm going up a half compared to what I would have gone over 1 and up 1. And I could set up a t-table and do this. Let's set it up. If I pick x and y, and just to show you that I was right, if I say -1, 0, and 1, -1 put in here would be +1. Cut in half is a half plus 2, so that's 2.5. If I put 0 in, this whole thing zeroes out, and so I get 2. And if I put 1 in, I get 2.5 again. And so those were the points that I was choosing. I know this thing is U-shape, so I kind of make it a little bit wider. And if you want to pick more points to be a little more accurate, that's perfectly okay. So then the next one, if we get something that looks like this, it says x squared that has moved 5 units down, 3 units left, and is 3 times narrower than the parent function. So when you see the words narrower or stretched, that means that you're multiplying by a number bigger than 3. So I just have to go through and start from my parent function of x squared. If I want to move it down 5 units, that means I subtract. Squared minus 5. There's down 5 units. I want to move it left 3 units. So left, it would be -3 originally, but it always looks opposite inside the function. So this is one that goes inside, and it looks opposite of what we see. And so there's so far, and then I want it 3 times narrower, so I want the thing skinnier. And so that means that I have to multiply, like we've been doing, by 3 to get my function. And so then I could graph it. And knowing all of this information, I could set up a t-table and plug in the same values I always do. -1, 0, and 1. And so -1 minus 3. -1 plus 3 is 2. That gives me 4. When I square it, 4 times 3 is 12. 12 minus 5 is 7. If I put 0 in, I get 9 times 3, which is 27, minus 5, which is 22. That's not good. And if I put 1 in, well, I get 1 plus 3, which is 4. 4 times 3, 4 squared is 16, times 3 is 48. And then I subtract 5 from that, and I end up with 43. Well, that's not good. I need to go the other way. I need to go into the -2, -3 to get the rest of my graph. If I plug -2 in here, I get 1 squared, which is 1, times 3, which is 3, and then I subtract 5, which would be -2. If I put 3 in, I get 0 in here, so -5. I'm almost done, because if I put -4 in, -4 is -1, but I square it. That gives me +1. Times 3 is 3, and then minus 5 is -2. So hopefully at this point you can kind of see where I'm going here, that if I go back 3, 1, 2, 3, and down 5, I will be at my lowest point. If I go back 2 and down 2, that's another point. And if I go back 4 and down 2, so you can see there's my parabola, and it's really skinny compared to what I've been doing before. And I could plot the other points that I did earlier, but most likely they're not very good, because the only one that really fits is -1 and 7, which would be like way up here somewhere. And so I was heading that way. I was heading that way to the point, but that's really what we're trying to do. So the trick to these is you got to practice writing out the functions. On the test, they're going to be that way too. So I'm going to slide one more up, and then that'll be the last one we're going to do. Write the equation of the graph that is that of x that has moved 4 units up and has the opposite slope as the parent function. So if I say y equals x as my parent function, if I'm going to move it 4 units up, that should ring a bell that you're going to add 4 to it. If I want the opposite slope, meaning going the opposite direction, what does that is a -1 in front of my x. And so there is my equation. Now, I'm not even going to set up a t-table, because I know how to plot this with slope-intercept form. It says start at 4, 1, 2, 3, 4, and go down 1 over 1, down 1 over 1, and then I can grab a straight line and graph it. So it doesn't matter what the graph looks like. It doesn't matter what the function is. Every time the function will follow the same behavior with these. Okay? So then we're at our out, and our out says sketch, draw and sketch a graph for x squared that is vertically compressed, it's wider, by a factor of 3. So that means we're going to multiply our parent function by 1/3. Then we have x, and they want it moved down 4 units, so outside the square, we're moving it down 4 units and reflected across the, okay, so we don't need anything else inside the function because we're not moving it left or right any. So we just want the thing flipped over the x-axis. So we're going to have x squared minus 4, and flipped over the x-axis means that it has to be a negative. And so if I'm sketching this thing, I'm going to go down 4, 1, 2, 3, 4, be right there. And if I want the thing wider, I've multiplied by 1/3, and so the graph is going to go real wide compared to what the original one would look like, and it would be something like that. So we'll practice more of this in class. I hope you've enjoyed this last webinar for translations. We will have more when we do the algebra unit. Thank you for listening.